parallel shaping distribution identification based on QPSK-assisted FFT for probabilistic shaping quant OWC systems. And I like to divide my presentation into the following 4 parts. Firstly, I would like to talk about the background and motivation. Recently, OFDM is widely used in OWC systems due to its high capacity, strong anti-interference ability, and simple equalization. To meet IMDD signal requirements, some new forms of optical OFDM schemes have been proposed, such as DACO-OFDM, ACO-OFDM, and PAM-DMT. To get closer to the channel capacity, probabilistic shaping technique has been proposed. Contrast that with traditional modulation. PS uses the lower energy inner constellation points more frequently and the higher energy outer constellation points less frequently, as shown in Figure 2, enabling it to deliver benefits like enhanced granularity, improved tolerance to noise, and baud rate flexibility. Meanwhile, the PS-enabled rate adaptive transmission offers the superior performance over other rate adaptive transmission techniques, such as hybrid QAM. However, the key to implementing a PS-based rate adaptive system is to design a hitless flexible transceiver to ensure proper demodulation, which have the capability to identify not only the modulation format, but also the shaping factor. More recently, several SDI methods for PSM QAM signals have been proposed. One category of SDI approaches is based on neural networks due to their ability of nonlinear characterization. The other category of SDI approaches typically based on GCHE, RAM, and so on. However, these methods are not optimal. In this paper, motivated by these previous works, we propose a novel SDI methods using digital FO loading and encoding shaping distribution as 4-bit information. The loaded digital FO can be estimated by finding the maximum magnitude of FFT after fourth power of the received symbols based on QPSK selection. Secondly, I would like to introduce the system model and proposed methods in our paper. We consider a PS-based ACO-OFDM indoor OWC system as shown in the diagram. At the transmitter, CCDM is used to obtain MQAM signals. After digital FO loading, to obtain a real-valued OFDM signal, the input IFFT signal needs to be Hermitian symmetry. Then we perform parallel to serial conversion and cyclic prefix insertion. Since negative signals cannot be transmitted in an IMDD system, we perform zero clipping to obtain the PS-ACO OFDM signal. At the receiver side, the reverse operation of the transmitter is performed. The indoor OWC channel properties can be represented by the corresponding pulse response, HT. Here, we take multi-reflection effect of the channel into account and use Monte Carlo ray tracer method to calculate HT. As for FO loading and SDI part, we first pre-encode the shaping distribution information into a codebook. At the transmitter end, digital FO loading is implemented according to the codebook. As we can see, in the proposed approach, there is a 1-for-1 correspondence between the loaded digital FO and the shaping distribution. That is, if the FO is correctly estimated, the shaping distribution is also correctly identified. Next, I would like to detail the digital FO loading. There are two steps involved. The first step is to define the FO loading codebook as shown in the table. The second step is to implement the 4-bit digital FO loading on each data block. Every 4096 QAM symbols are divided into a data block, which contains 4 parts. For each part, we implement the 1-bit DFOL as shown in the formula. Now that we have an idea of DFOL, let's turn our attention to FFT-FOE based on QPSK selection, which is used in SDI part. For traditional non-PS-QAM signals, it's fourth-order non-circular. This results in an intensity peak in the discrete spectrum after FFT. However, for PS-QAM signals, FFT-FOE does not work well. In order to guarantee the performance of FFT-FOE, we use a radius threshold to select inner QPSK symbols. After QPSK selection, we can perform FFT-FOE. Then comes to the last step. We set a decoding threshold for recovering the FO information bits. If the estimated FO value is lower than the threshold, the estimated code is 0, otherwise it would be 1. Let's turn to the next issue, numerical results. Here, we list simulation parameters in the table, and we plot corresponding digital FO loading values of 4 blocks for each shaping rate. Also, we can see that the decision threshold is set as 25 trillion Hertz, as shown in red line of the figure. Then, from these two figures, we can see that the discrete frequency spectrum with coding 1 and the coding 0 is different. Consequently, we can estimate FO by FFT. From this figure, we can observe that 8 shaping rates are correctly identified. Meanwhile, it shows that the accuracy of SDI increases rapidly from 0 to 1 as the ASNR increases. For a signal of a certain modulation order, such as 16 QAM, the higher the shaping rate with smaller constellation entropy, the lower the SNR required to ensure a 100% success rate. This is because the effective SNR is higher for strongly shaped signals with small entropy. Now we come to the last part, conclusion. The proposed SDI for PSM QAM signals is a promising blind identification method to recognize shaping rate and modulation format. A method does not require additional complexity, which can be easily implemented on the transceiver side. Numerical results shows that it has a good performance using only a small number of QAM symbols. That's all for my presentation. Thanks for your listening.
Okay, thanks, Hongye Li, for a nice presentation. So you are on site, right? The presenter is on site?
Yes.
Okay, yeah. So now it's open for the questions. So any on-site or online questions? So first I have questions. So in your scheme, you propose the identification for the probability shaping. So, and here you compare with edge shaping rates. You say you can correctly identify it. But my question is, why not just send the information to share to transmitter and receiver to know which shaping rates you are used? Because you only have 8 rates, right? So 8 rates, you can just send the 3 bits after a long period. It's not the very large overhead, right? So can you comment on that?
Yeah, thank you. We want to propose a blind identification. That means we don't need to send the information first, but instead of analyzing the signals and to know the shipping rates.
Okay, but so you mean you want to do the blind DSP, but using some a little even low complexity, but still need some algorithm like FFT to recover the signal or identify signal, right? So trade off the overhead and the DSP complexity. Right. Okay. So I think it's your motivation clear and the results also nice. So it's if there no other questions online on site, now thanks for the presenter again. Let's move to the next one.
Thank
So
you.
the next, yeah. So next one is